Get started. Happy Wednesday, and welcome back to probabilistic world. No one's really in that world, of course. But welcome back to the class of probability and stochastic processes. And let's see what we're gonna do today. Let's see what we did last class first, then connect it to this class. Okay, let's set a stage. Last class, you learned about Markov sequence. Markov is famous Russian mathematician. Was, I think, I'm not sure. I think he passed away. Anyway, Markov did lots of work, but he couldn't believe how his work right now used in so many applications like machine learning, artificial intelligence, and reinforcement learning specifically. He couldn't think this Markov property can work in this kind of application. Anyway, Markov is just a property of the system. If we are saying a system is Markov, means what? Any you remember? You remember what Markov means in a system when we say, okay, this system is Markov? Yes?
Its time is discrete.
It's time discrete? Time is discrete in sequential, it's not specifically. It's not Markov process, yes?
It has discrete states.
What?
It has a discrete state.
Discrete state, no, that's not true. But no, the main point of being a system Markov in general.
Memory?
Being memoryless, exactly. Being memoryless means Markov. Means the state of the now, a state of future is not depend on past. That means Markov property. So Markov property means memoryless. That's the main part. Of course, actually timing, when we say is a Markov sequence, it means the time is discrete. So we started with Markov sequence. Let's see what we did last class. Let's change the color to blue. So we started talking about Markov sequence. We said in Markov sequence, time is discrete time. And then the property was that the memoryless property is the main property of Markov in general. If we say a system is Markov, if a sequence is a Markov, if whatever is Markov means probability of, for example, xk plus 1 given xk and xk minus 1 and so forth is equal to just probability of xk plus 1 given xk. That means memoryless. So this is the main characteristic of Markov systems. So we talked about Markov sequence. We said, okay, Markov sequence is time sequence. Time is discrete. And then we moved to Markov chain last class. We said Markov chain, that as you explained, Markov chain is not just time discrete. What about a state be discrete too? like we have limited number of states, like for example in a cloud, in a like rain system, weather system, we had rain, we had cloud, and we had sun. That it made a Markov chain. That's called Markov chain. In Markov chain, we have actually states. We have transition between states, transition probability, and we also have a steady state. Last class, we also talked about that part. So about Markov chain, so we talk about a state diagram. First one, a state diagram. Yes. Yeah. First, we talk about Markov state diagram, and then we talked about what else? Transition matrix, 2, transition probability that can change to transition matrix, that was P. Like for example, probability of being rain and stay rain is, for example, 0.1, 0.8, and 0.1, and we set, and so forth, and we set for each row we need to have actually total probability working, so this summation need to be 1. This was for transition matrix. We call that transition matrix. So we had that. What else we had about Markov chain? A steady state. Yes. We also talked about the steady state. We said a steady state is a state that is a steady. A state is not changing anymore. If we repeat and repeat, it's going to go in that state. The steady state is the time that a state of the system in K is equal to a state in K minus 1. In this case, pi is equal to pi p, if p is a transition matrix. And with this, you can find that state. Even you can find that state. For example, for an island that is sometimes rainy, sometimes clear, sometimes sunny, you want to see what is the distribution of being sunny all the time. You can find that based off a steady state. Okay, we talk about this stuff, and then we said, okay, Markov sequence, Markov chain, and we said, okay, let's go more broader, make it Markov model. Any system. Okay, let's go to, okay, a Markov model was a model that just has characteristic of Markovian. If a model has this characteristic, that model called Markov actually model. We said, I shouldn't come this way, but anyway, we said we have 3 types of Markov models. We have visible Markov model. Do you remember what was visible Markov model?
We can see the process.
We can see we can see the state. The state is visible. When the state is visible, like in that weather example, a state is sunny, rainy, cloudy, that state is visible. So that's a visible Markov model. We also have hidden Markov model. So in hidden Markov model, for sure, the state is hidden. A state is not visible directly. You can see the output of the system, but the state is not is behind, like maze a robot that moving in a maze. And robot wants to find the door to go, but the state of this system is a position, but it's not visible. We are not carrying a position. It cares, of course, but the robot has two sensors to just find a way to go, or the doors or obstacles. And based off these two sensors, find a way to go out. But the position is very important to make that decision, but it's not visible. It's not something that is behind. So that system called hidden Markov model. Most of localization system like Kalman filter that you were doing, that's a the Markov model, but hidden Markov model. So this is two systems that we talk class. However, we just describe that, go deep. But today we want to go another application that is Markov decision process. That is very useful to know because it's actually mathematically explain decision making under uncertainty. When you want to have decision making under uncertainty, when the system is not certain, but still you want to make decision, Markov decision process is the method that you always can use. Not always, but most of the time you can use. So Markov decision process is mathematically explain that, how you can make decision. Okay, I'm talking about making decision. Who make decision? Who? What?
The agent.
Agent, exactly. The robot, the agent make decision. So we have agent. In top of that, we have somebody to make decision. It's not me. It's agent. Who can define agent? What is the agent? Agent, in AI, we probably know that. Any idea coming to however, it's obvious what agent means because it's in their name. Agency, you know. Tell me, anything coming to your mind? What agent means? Yes?
Is it just anything with the ability to make decisions?
Yeah, exactly. It's able to make decision by itself. Doesn't make you to make decision for it. It can make decision for itself. If it's an autonomous system, it can make decision by itself. So that makes it an agent. Agent not supposed to be hardware all the time, can be a software. Like new AI systems they're gonna be agent based soon. However, they are. I think ChatGPT already has that. I'm not sure, but I think they were talking about that a lot, that they want to make it agent. So it means what? It means if I want to, for example, do something like, for example, instead of going to my email and give my email and give it to ChatGPT to, for example, respond one, I can say, okay, ChatGPT, go check my email, and whatever you think is need to answer, answer it by yourself. Just give me the result. He's gonna say, sure, sir. And I do that's agent. And whatever you're gonna bring up for me is based off its preferences. However, I can give lots of information before, and probably that AI agent knows me enough to know, for example, if, for example, I get some emails from somewhere that is not very like advertisement or something, don't answer those. You need to bring that up and just bring the most important parts up to me and say, okay, this is most important emails that you need to take a look. Are you agree to send it? I said, sure, or no, keep it. I need to check it out. That's called agent. And it's just beginning. Agent can be an autonomous robot that is in a war field and make decision to shoot or not by itself. Is it enemy or friend? That makes it scary to make decision by itself. Imagine an agent controlling, I don't know, shooting a missile or atomic bomb. By itself, can make decision by itself. So this is the time that I need to shoot. That's scary. So giving actually this ability to AI or computer or algorithm to make decision, make agency. And however, it make decision based off so many other things. It's not make its decision easily, especially for some critical safety decisions. It's not make them so fast. It probably need to check so many things and then make decision. And that's the time or the place that Markov decision process is one of the methods that can be used. So many applications. So let's see how you can make decision. Our agent can make decision in uncertainty. So in Markov decision process, you, in addition to a state, state S0, S1, S2, for example, in addition to state and transition, you have some other things too, because you have agent. So agent need actually some actions. Okay, for actions, let show that different way. Maybe this is. We have state 0 and action. And we have some transition. Transition is the same. Probability of moving from one state to another state. Like action state can be like intermediate state. Can consider as an intermediate state. Oh. Like you are in a state, for example, 2, and make this action. So this make another state diagram. In this state diagram, you have a state, you have action, you have transition matrix, or transition probability of transition to something to the other that we had it before as well. We also have reward. Reward means how much you get reward or get punished to move from this state to another state. And also we have another variable that actually showing discount factor. It's called discount factor. That's showing how much you like to get reward right away than future. You like to get $1 now or $5 1 year from now. That's gamma. Is it gamma? Yeah. That's specified. That's called discount factor. Okay, let's clean up this. We have a better. So we have this definition. State, actions. So let I write it again. State, actions, transition, probability, reward, and what was that? Discounting factor. Discounting factor. Okay, so with these 5 numbers, this actually 5 numbers, they are not numbers, they are different like arrays. This tuple, we can model a Markov decision process. So what is objective? What is objective? We have reward. So the objective part is we want to maximize reward or minimize cost. So you can guess what is how we can find the best actions. So the best actions, because we have action, the best action is the action that what? Maximize reward, yes? The best action is the action that maximize not just reward now, but expected cumulative or additive reward, but we can also discount this reward by time. So we can actually make that one. So in general, we want to have expected value discounted. When we say discounted means this discount factor is something less than 1. Like for example, is 1/6. For example, is between 0 and 1. And we sum it up, t from 0 to infinity, and we add all the rewards of what? Being in a state t, and do action t to go to a state t plus 1. We add all of those rewards together and make average, and that's going to be utility. Utility means this, and we want to maximize utility. But this utility is based off some mapping or decisions or policy. Why? That's a policy. We also have policy here. So policy is like a map for you. So based off that policy that you are choosing, you add all of those rewards that you're going to get, discount them by that factor, gamma, discount it by gamma. That is a number between 0 and 1. As you can see, we multiply that. We make a power of t of that. When t become bigger, that value become less and less and less. So it means when you are going to infinity, the reward gets lower value. The reward now has higher value than 2 days from now, because that factor discounted makes it lower. Okay? So this is utility. So based off this function, you can see which policy is the best. Policy showing decision. Which decision you want to make is based off that policy. We're going to see what is policy, okay? Don't worry. So we saw some new stuff. Action, agent. We had transition, we had state. Reward is obvious, reward. Discounting factor. So if this go together, make a system that system is Markov decision system or Markov decision process system. So, and it's basic for decision making under uncertainty. Okay. Let's have example. Let's see if there is anything else I add in this. Oh, let I clean this up to show this. So the objective, the agent seeks a policy that maximizes the expected cumulative reward. So you can guess that what is the purpose of Markov decision process now based off this page. What is the purpose? What we want to find? What is the objective? Albert mentioned that. But I want you to tell me. I want to see, did you get that? What is the objective in Markov decision process? Yes?
Optimization.
Optimization to find what? Yes, of course, it's optimization. To find what? What is the objective to find? What we want to find? Yes?
The highest reward for the decision.
Highest reward based, we want to find policy. The agent seeks a policy. We want to find the policy. Agent wants to find policy. Policy is that map. So the idea is to find a policy. Yes, we are doing maximization. We want to maximize rewards. We want to maximize utility to what? Maximize utility for what? So maximize, we are arg max u of policy for policy. So this is going to give us the policy, optimal policy. The policy is the point. We want to see what is the map. When the robot is here, we want to see what is the policy of moving to find a door. So the policy is going to give us the map. It's telling if you go this way, it's going to be maximize utility. So go this way. So that's showing the policy. So policy is like a map, but is again a stochastic map. Is not. It has some probability based because nothing is in this environment certain, and Markov decision process can model that uncertainty inside. So let's see how. Yeah, and we want to, this is the utility that you already explained. Any question about this? Okay, go back to this one. Okay, let's see, let's have example. Oops, myself now. Okay, let's have example. This is a game. We can play this game, but we don't have dice. Anyway, this is a game. Imagine we have a game called a Stay or Quit. This is very actually famous game for teaching Markov decision process. So they always talk about that. So let's go for that because it's very showing the fundamental parts of Markov decision process. Let's do that. So we have we want to play this game. We have a dice, and first we ask, are you gonna play, or are you in? Or not. If you are saying, no, I'm not in, you're going to get $10 and go. Okay? But if you say, I'm in, we say, okay, you give $4. You earn $4, and you can play another role. But staying in a game is based off the die that you are actually become 3 to 6. And between 3 to 6 means there is chance of 2/3 to stay in a game and 1/3 to lose the game and get out. So you have normally in, a state in, and a state end. If you be in and wants to stay, you get $4. And the probability of getting $4 is 1/3. And lose. And if you say, I want to stay, and probability of staying again means get 3 to 6 is again 2/3. So again you get $4. If you quit right away, you are in and quit. You get $10, 100% with probability of 1. So that's the system that you have. You have two main states and two kind of half a state. We call it a state action. This is how we model this system. So we have two states, in and out. In means staying inside the game, or out. If you get out, you're just gonna get $10 and done. But if you get in, you have chance to play again and again with 2/3 probability. So are you gonna stay or you're gonna quit? Don't look at the computation that I did. Of course, after computing expected utility, you can see, oh, you can earn $12 if it stay. This is how gamblers play. They think if they stay, they're gonna win. But in gambling situation, these probabilities are not always like that. Here we know the probability of staying has more chance to win than fail. Because if you stay with more probability, you're gonna stay again. And we can compute that. We can compute that expected utility to see, do we need to stay or not? So if the gamblers know these probabilistic methods, they always can make better decision. But gambling, unfortunately, becomes like a habit. They want to do it anyway. They don't do calculation. They just want to randomly make decision. Okay, so what is 1/3 means? If first time you lose. Oh, I didn't. Oh, yes, I think I mentioned this stuff. Okay, if the first one you lose, you just get $4 and go. First, lose. So you're gonna get $4, and the probability of losing in 1/3. So it's gonna be this. If second round lose second round. If you second round lose, you already earned $8, and you got first $4 with this probability, a second one with 2/3. And if you go for third round and fourth round and forever, this just 2/3 is going to repeat. So you're just going to have a square of that or cube of that and so forth. And if you add them up, it's going to be something around $12. This is average, you know, we can't say it's going to be 100% that. Maybe you just lose in first round and just get $4. But if you stay in a game, you have chance to get that much money. So that's actually expected reward. That's called expected reward. Expected. It's you expect to get that reward. That's why this everything probabilistic. It still is probabilistic in this environment. Even though we make decision, this decision is not certain 100%. It's all based off probabilistic formula and ideas. And that's why a Markov decision process is a mathematical method of modeling models under uncertainty. Okay, so this is how we find expected utility. So here, it's just calling myself. Okay, here, yes, I draw already this. So this is a state diagram for Markov decision process for dice game. As you can see, you have a states in and out or in and end. Actions, stay and quit. And transitions, you have transition is if you stay with probability of 2/3, you continue staying. And if you stay and game end with probability of 1/3, so that's the transition probability T. And also you have reward that is $4 and $10. And you have policy. Okay, so what is the policy? Staying or quitting. That's policy. Policy means after that much computation and computing expected reward, we get the point that, okay, let us stay. That's the policy. And all of these algorithms or methods or model is to find the best policy. To agent make better decision. Imagine agent playing this game. An agent wants to make decision. Do I need to stay or leave? However, this game is so simple, but it can be more complicated, much more. Sometimes quitting much is better, decision. Okay. Transition probability. Oh, it still is going by itself. Don't know why. Let's stay. Yes, okay, that is stay in a page. Transition probability, we already explained that. Transition probability showing what is the probability being in a state 0 and do this action to go to state S prime, for example. So this is transition probability. Showing if you are in a state 0, for example, and do this action, gonna go to a state 1. This is not 100%, still is probabilistic. So the probability of being in a state S0, and take that action and move to a state S prime. That's called transition probability. So in this example, example of stay and quit, if you are in and quit, probability is 1. If you are in and get the make action stay action, if you get this action and next state becomes in with probability of 2/3 and end with probability of 1/3. But the things that I want to mention here is this. You still have total theorem. So it means for each action, the sum of all probability need to be 1. If you want to stay, if you get the policy of staying and stay in the game, if you lose or if you win, add up together need to be 1. So that's something that we always need to consider. Okay, so that's transition probability. That is something simple. Let's do a solution for solution for MDP. As I mentioned, solution for MDP is policy. So the reason of modeling a system with Markov decision process is to find the best policy. Best policy means the policy that maximizes reward or utility and minimize cost. How we can evaluate a policy. That's something that we need to consider. Okay, first of all, in this picture is like the grid. It's like a maze, for example. Imagine this is a maze. And that's the policy. So the policy showing this map. However, here we're going to have some probability too. So they're going to have some colors. But here we don't have that. But in here, this map, we have some obstacles, those black parts, obstacle. We have some parts that probably if you go there, you're going to lose lots of reward. Like here, for example, is -10, for example. And here is +10. So you're going to get lots of reward if you go to that state. They are a state. Here we have so many states, like 12 states. Some states not allowed, like for example that obstacle, we're not able to go that. Some states, if we go, we're gonna lose lots of things. And some states are our goal. So what is the goal? To everybody go to that diamond. That's the goal. Going to the diamond is the goal. So after evaluating the policies and updating the policies and optimizing this system, we can say if we are in here, for example, if the state is here, it's better to go that way because it's the shortest way to go to the diamond. And if we are, for example, here, the best way is to, because we don't have other choice, we need to go just this way. Or if we are here, it's better to go that way. So that map is the policy. So you want to find this. And this is everything, it's going to give you decision making. So right now, with this policy, agent knows what to do when, as much as agent knows where it is in this maze, or in this grid, it can make decision which direction need to go, which action need to choose. But to find this, we need optimization. And right now, I want to go through that optimizing method and tell you how we can evaluate a policy and how we can optimize a policy. Probably we need to maximize utility. So we need to make a utility function that we call it value function later, and we maximize that respect to policy. So find the best policy that maximizes that. That's normally the method. And because our action is the future actions, it's kind of dynamic programming. Have you had dynamic programming before? No? Have you heard about dynamic programming? Yes, it's maybe data structure. Have you had data structure? Yes, in data structure, advanced data structure mostly, or algorithm design, you have dynamic programming. But I'm not going to go in those parts. Don't worry about that. It's not something, it's not related. But to solve that is kind of that. But you just can open, because dynamic programming is like a recursive algorithm. But you can open the loop. And here is, I'm going to show you the algorithm. It's very simple. Okay, so that's the definition of policy. So the policy is mapping from each state to action. So policy is a function in general. So it means policy of a state give you action. Policy of a state give you action. So policy of, for example, a state be this number. This has some number. For example, this is x and y. This is a state 3. If here is start with 0, it's 3 by 3. It's 3 by 3. If we are in a state 3 by 3, the action is moving up. So here we have actions is this, this, and this. This is, we have 4 actions. We can put a number for them like 0, 0, 0, 1, 1, 0, 1, 1, for example. We give them some code or number, 0, 1, 2, 3. And these actions is based off the position that we are, right? What give that to us? Policy. Optimized policy. This is the max, like the optimal policy. So to get that policy, we need to evaluate policy and optimize it. We're going to see that soon. And in simple term, a policy tells the agent what action to take. What action to take in each situation. Okay. Any question about this map? So maybe this come to your mind. Oh my God, I can design a game. Yes. One of the best way to write a game is using MDP. Because in the game, we have agent. The engine of that game can act as an agent and play, and the other agent is you. So there is 2 agents playing together, and you want to make best decision, and the computer wants to make best decision too. And this is 2 decisions against each other to see which one is better. Because they both are stochastic, they both not certain. This is gonna make actually a good game. Let's see how we can evaluate a policy. So as we explained, we have utility. So utility, generally speaking, if I don't go to the details, it can be similar to the value function. So the value function gonna be like expected, discounted, cumulative reward. Expected, discounted, cumulative reward. This is expected, it means mean. Discarded, it means disgusted. Discounted, sorry, discounted. So it means we give more value to rewards that happen right now, later. And then, oh my God, time is past, like flying. Anyway, so this is what we need to do. We need to maximize this. So because I don't want to continue that, let's finish this. So the policy iteration is a method. It's mostly it's just computing this value, is the same value with a little change, and find the maximum. We don't need to know details. I did that for the maze algorithm. This is the start of maze. It start with this. After second iteration, it find good policies. And after 3 iterations, find the optimal policy. This is the optimal policy, showing this is terminals, and this is showing which direction we go and like the probabilities and rewards and whatever. So this is very simple. We don't want to know too much details. I just wanted to tell you the application of Markov models. Okay, next class, we're going to talk about actually power spectrum density. We want to move to frequency domain. Okay, have a good day.
We plan for the last one.
Yeah, but for